All right, so thank you very much, Amy, for the introduction. I'm very happy with this opportunity to talk with you guys about our work here. So I am Philipe Dias. Good afternoon to some of you, maybe good morning for others. I'm not sure what is the time zone for everyone. So I'm going to be talking about our research on bloom intensity estimation. And I expect that we have an audience here that is coming from like different fields, maybe more people from the machine learning side, more people from the precision agriculture side. So I tried to structure this talk to provide enough information and background for these different types of audience. So hopefully everyone can follow here. So first I will talk about why we care about bloom intensity estimation, the types of data sets that we annotated and made publicly available, the types of approach that we have been using for fruit detection, fruit flower detection, using mostly convolutional neural networks. So I'll introduce a bit the concept of those networks, why do they work, what are they good for, which kind of limitations they do have, and how we have been trying to use these networks for our application and to overcome the limitations of this network, specifically a segmentation refinement algorithm that we developed. What is our current status on multi-species fruit flower segmentation using these approaches? And also talk at the end about annotation tool that we developed for annotating our data sets that we are making publicly available as well. So first of all, bloom intensity estimation, what is this? Why do we care about this? Bloom intensity is essentially the number of flowers that you have in the orchards during your early growing season. And this is important to guide processes such as this one illustrated in the animation here, which is called thinning. You need to get rid of some of the flowers because you need to avoid scenarios like this, where you would have fruits growing very next to each other, so they wouldn't be reaching the proper size, shape, and taste, and so on, that you desire for them to be commercial. And in addition to that, if you do know how many flowers you have in your early growing season, you have a pretty good estimation of what's going to be your final yield. So you can correlate this kind of information to estimate what's your final yield to prepare your marketing, benefit the packing houses, and so on. So how do people currently do that? The problem is that right now we rely on people walking through those orchards, scenarios like the one illustrated in this image, trying to estimate visually how many flowers you do have. And the thing is that even for this static example here, it's pretty hard for us to agree where are all the flowers here, which are illustrated in blue here in this example. So what happens is that this is a procedure that's very time consuming, this is very prone to errors, and you're gonna be checking only a few of your trees in your environment, so you don't have too many tree-specific information. So our goal is essentially to develop at a low-cost, user-friendly, like an app, illustrated here, for instance, where you could have a tablet taking a picture of your tree, and automatically get a detection and a counting of the amount of flowers that you have in this tree, in this image. That would mean an algorithm with the deep learning approach running on the cloud, and then you simply get instantly the output, the information that you want in your tablet. And in the long term, if we do have a good detection segmentation of the flowers, you can also think about automatizing the whole process of thinning and maybe doing the pollination of the flowers. So here's another example. What it shows is that we want something general that you don't need to keep tuning for different environments or situations of illumination, something this is pretty easy to use. So are we the first ones trying to automatize this? No. But the thing is that it's actually the limitations that you do have in the previous approach are limitations from the computer vision in general. People try to use mostly what we call hand-engineered features or handcrafted features. There would be someone maybe trying to develop some sort of texture detector, or for example, in this case of the flowers, people would be relying mostly in detecting specific colors of the flowers. So if you have an apple flower, you search for white structures, as the ones illustrated here in the upper left example. But then if you simply have the same flowers into different illumination conditions, you have already different values, so your approach won't work anymore. Even worse, if you go to a different flower species, like the peach flower illustrated here, that is pink, that changes completely the type of color characteristics that you have, so a model suitable for the apple wouldn't work for peaches. And then what happened recently with the development of the deep learning approaches is that essentially they allow you to replace this idea of hand engineering features by something that you can learn by means of training. So how does that work? In a very brief explanation here about neural networks, in case someone is not familiar with, the neural name aspect comes from what we have in this diagram here, that you have essentially a representation where you have multiple inputs and you are learning weights. These circles here with the W inside. Those weights are the parameters that you're going to adjust according to your task. So essentially you can have the inputs like the pixels of your image, for instance, and then you have examples of what should be the output of your algorithm for these inputs. And then those neurons, based on the inputs multiplying by the weights and some sort, they are added up. You have some activation. They either activate or not based on the inputs. And you can stack a bunch of those neurons, one after the other, on top of the other, so that you have a network of those neurons that have thousands or millions of parameters that can be tuned according to your task, to the examples that you have, so that you have an input, you have an output, you compute the error, you backpropagate this error, and you keep adjusting the weights until you have a network that does the task that you are searching for. What we use then for this image understanding task is what we call the convolutional neural networks. So the difference of the convolutional aspect is that you're going to be evaluating specific patches of the image at a time, not the whole image at once. So you have like a sliding window where the weights here are essentially this 3x3 block that is sliding over the image. So you're learning these weights that essentially they are learning to extract features like edges at your lower level of features, lower level of context. So the interesting thing then is that you combine those edges by stacking more layers one after the other, from left to right, into more complex object spines. So we have, for example, this example here on face detection, that by learning windows, feature extractors, one on top of the other, start to combine them into increasingly complex structures, from edges to object parts, and finally to what is the description of a face. This is what the networks can do that is different from what we had before. This is the key aspect, that they learn what we call the hierarchical features. So by means of training, they can extract features that was simply feasible to describe manually to come up with those features. These networks were first used for the task that we call image classification. So image classification essentially tries to answer the questions like, what do I have in an image? For example, do I have a cat? Do I have person? Do I have people? So this first model called AlexNet was developed for the ImageNet dataset challenge with thousands of classes and more than a million images. It was introduced in 2012 and already decreased the error rate that you have in this test by about 10% compared to the previous approaches. And long story short, right now, we have errors of below 4%, like 3.5%, which, to give you some reference, the human performance expected in this kind of task is about 5.1% of error. So we could say it's pretty much a problem solved. It's kind of a superhuman performance achieved by those networks. But that doesn't mean that we have solved all kinds of problems in the image understanding scenario, because we are talking here just about image classification, and this is sort of the simplest task. We have more increasingly complex tasks, which are like classification plus localization, or even more object detection, where you can have multiple instances of certain objects. Say, for instance, here the cat, you have two cats, and you want to say exactly where they are, to have a box around them. And then to tackle this kind of problem, which is more related to our our goal of detecting flowers for bloom intensity estimation, that people have been introducing network models called RCNNs, which is what I'm going to be talking about now, specifically for our attempt for flower detection. So I'm going to introduce now our first model that we developed for flower detection, which is based on superpixels and convolutional neural networks. The idea is you have those classification networks that can tell you what you do have or not in an image. So if you want to detect where those things are in the image, what you can do is to generate what we call region proposals. One way of generating this is splitting the image into smaller parts like superpixels. Superpixels essentially are clusters of pixels that are nearby each other and share similar colors, like it's illustrated here by these boundaries in pink. So we have, for example, this superpixel attaching well to our flower in this image. And what we do is that we evaluate each superpixel individually using a classification network. So we build portraits around each of those superpixels. And then we evaluate them using a classification network. The classification network that we use is a network that we perform what we call fine-tunings, that we make this network specifically sensitive to flowers. So it can differentiate between portraits with flowers or without flowers. And then at the end, we have PCA and SVM for classification. I won't talk too much about that because the detail in the classification here is just a matter of a little bit like 1% more in terms of accuracy, but the key thing is what this network can provide you in terms of embedded space of feature representation to classify flowers or not flowers. Let's briefly mention how we fine-tuned this network to be flower sensitive. I will go into more details for a second method, like on the training of the network, but one interesting thing to note here is that our data set that we initially annotate based on the superpixels, it contained only about 4% of its composition actually having flowers. So that means we had a lot of examples of negative background and just a few of positives of flowers. So we had to do what we call data augmentation by mirroring the positive examples with flowers, both horizontally and vertically. So then we have 4 times the original amount that we have of portraits with flowers. That allows us to train the network and obtain a network that can generate a feature space like this. So this diagram here, we illustrate how the network maps those different inputs into a feature space where you can easily separate between flowers in the upper left corner, or ground in the upper right corner, or leaves in the lower right corner. So that's why I mentioned that essentially the classifier doesn't mean too much here, because even if you trace like a simple line in this feature space, you can already differentiate between the flowers and the other types of structures. Similarly, if you add another projection from the feature space generated by CNN, you can then differentiate between patches of the sky in the background and what you have as flowers and other structures. Again, simply tracing a line is already sufficient to differentiate these two categories. So with these methods, with superpixels, decision proposals, and a classification network, we already obtain results like illustrated here in the video. What is in blue is correct detections. What is in pink are things that were detected as flowers but shouldn't be. What is in red are flowers that were not detected. So we see that mostly we have blue things here. Good. And then in terms of metrics, we had an F1 measure for the images not seen from this data set. So we trained it with a part of this data set, evaluating another part that was not seen from the network. We had an F1 measure of above 90%. So for those of you that don't remember what is the F1, it's essentially combining precision recall. As you have precision recall curve, you get the point nearest the optimal recall based saying how many of the true positives you're getting, what is your precision in terms of how many false positives you have. So it's significantly better than the baseline approaches, which are based on your own color. And the nice thing is that it works fairly well already for unseen scenarios like a different flower data set illustrated here in the middle, or even for peach flowers, which are significantly different in terms of color. But that doesn't mean that we solve the problem. The thing is that, as I said, these methods rely on superpixels as region proposals, and the superpixels are not perfect. So we have examples like these ones, which are superpixels that contain both parts of flower and parts of the background. So they're going to be mapped by the network in this feature space into a region of uncertainty that you cannot have a good classification of either this is a flower or not. So it's intrinsically a limitation of this approach. And this is a limitation of region proposals in general that people have been exploring alternative approaches for overcoming this kind of limitation. So here I will make it the first stop in case anyone has some quick questions about this first part. At the end, you have the Q&A as well, but I think it's good to have a break right now.
Okay, so we have one question, Felipe. Where did you get your data sets?
So yeah, I'm going to be elaborating a little bit further in data sets for our second approach because we had to actually annotate these data sets. We made them publicly available. For this method I talked about first, we annotated only based on superpixels. But right now we made available annotation at a pixel accurate, pixel level. So that's what led us to develop a tool for annotation that we'll talk about more at the end of the presentation.
Okay. And this is Henry Medeiros. So he says you may want to mention that they were collected at USDA ARS in West Virginia too. So this is Amy. So I'm a co-author on some of these papers too. So I collected some of these data sets, but Felipe is presenting, so I was letting him.
Thank you for the information that I forgot, the important information that I forgot to mention.
Yeah, so you're presenting, so I'm letting you talk about all of that. So I will mention that if you're curious about the material in the talk, so on the website, we give a lot of the material that is in the webinars. We post the links to the material. So for this webinar and our previous webinar, Zach Pesamenti and Trenton Taper's webinar, we have all that material for you. So you know, it's pretty easy to find and they're open access versions. So you can just go to the IEEE-AGRA.com website and the webinars, it's written up and you can access that material there. Okay, here's another question. You just said it and maybe I missed the solution in your comment, but when you have a superpixel that is a bunch of flowers combined, it's a limitation of the superpixel method. But what are the solutions, new methods doing differently that you aren't?
So yeah, it's intrinsic limitation is essentially what you're gonna have is some sort of a score that's gonna be around 0.5 if you think about a normalized score. So that's why the second version that I will mention is more like trying to get rid of the region proposals or the superpixels at all. Because if you have bad superpixels, that there isn't much you can do essentially.
Okay. And let's make this the last question for this section is how much time did it take to train the network for this part one section?
So yeah, we trained a model that was pre-trained before on the ImageNet, and then we for saliency detection afterwards, and then we fine-tuned it for the flowers with like 10,000 iterations. It didn't take much long. So I'll provide a little bit, there are more details in the paper, I'll provide a little bit more detail, which are the procedures that we used for fine-tuning for the second method was also similar in terms of the policy rate that we used. And then there is also information in the paper about the type of how many portrait examples we have and everything.
Okay. Okay, I said it was the last one, but I'll do one more because it's quick. What kind of hardware were you using? Do you remember for the first? Or
sure,
maybe
yeah, it was a GPU, an NVIDIA one was the K80 at that time.
Oh, okay, Henry's answering. It's a.
Yeah, the one that Henry mentioned is what we use now for our second method, the one that we'll be talking a little bit more.
Okay, the Pascal P6000.
Yeah, exactly.
Okay.
But we got more recently.
Okay. So let's move to the second part of your talk.
All right. So as I mentioned, we have these problems with the region proposal networks. So you can think about two ways of fixing this problem of overcome this limitation. You either extract better region proposals by like learning, for example, region proposal neural networks that specifically tuned to do this kind of region proposal generation, or you can try to get rid of the region proposals at all. How? So there is one concept called fully convolutional networks where essentially they try to make a simple change, if you think about it, because the image classification networks, the structure is like illustrated here, where at the end you have what we call fully connected layers. So at the end you have, for example, you have a data set with 1,000 possible classes, you have one output unit computing the level of confidence that the network have that a certain category is present in your image or not. So for example, person and a bicycle here in this image. So the idea is simply let's get rid of those fully connected layers and replace them by further convolutions so that we can simply get then at the end already the map of the put activations for where each object is in this image. You have segmentation masks. And it does work fairly well, but what you have is a very coarse mask. So why does that happen? And this happens to be an intrinsic limitation of this kind of structure of those classification networks. So as I said, they can extract the hierarchical features by evaluating different levels of context in this image. So that means different levels of zooming in or zooming out in your image. The way that this is done is that you have two options to do that. The first would be you evaluate with larger windows. So here we have first in this image illustrated in the red block here, what would be a small window evaluating a very low level, a very detailed level in your image. And you could think about making this window larger and larger to evaluate larger parts of the image. But that would mean including more parameters to be learned. And this is a problem because even the most simple networks like the AlexNet here, that already have millions of parameters to be learned, and that requires thousands of images. That's why only recently this network became feasible for this kind of test, because now you have enough data and enough GPU to be training those networks. So you don't want to have more parameters, you don't want to increase the image. So what those networks do is that they downsample the image and keep the window size the same. So that's something like going further and downsampling more and more your image. And this way they successfully can evaluate different levels of context and learn the hierarchical features. This works very well for the image classification test because you just want to see what you have in the image, regardless of like the translation of this object inside the image. But that becomes a problem if you want to actually to have pixel accurate segmentation for where those things are in the image. So you would have essentially more and more a blurry version of what is your input, what is your image, and even if we try to annotate what is the segmentation in this downsampled image, we're going to have a coarse mask. So this is where the limitation comes from. Different strategies have been explored trying to overcome this limitation, including making like larger windows, but instead of adding parameters on them, to pad those windows with zeros. That's called a true convolutions, or you can try to guide a upsampling based on how was the downsampling done. These things do improve significantly with the coarse segmentation that I showed before, but they still are not as fine as we would like them to be. They're still fairly coarse. So what people use as well are post-processing strategies like conditional random fields, where you have an iterative process of refining the output that you get from the network, or learning specific refinement network to do this kind of refinement of your segmentation to attach better to the edges of the object. But both of these methods, they require optimization for your specific data set and for your specific network that you are using. So they're not very general in that sense. They work well, but they need to keep tuning for every specific scenario you have. So that's what motivated us to come up with a method that we call the region growing refinement, the RGR. The idea here is that we have available as input the image and the classification, the score map predicted by regardless which network you are using. So for example, here we have the image of an airplane, and then we have the prediction of a pre-trained network saying like its confidence level where the airplane is in this image. And we do know that, yes, if we do like a hard threshold here, you're gonna have a coarse segmentation, but that doesn't mean that we don't have information that we can trust here. We do have regions of high confidence here, which are, for example, in this score map, we illustrate it's a score map ranging from dark blue, which is corresponding to 0, and then the dark red is corresponding to 1. So you have from 0 to 1 the level of confidence that the network has that this specific pixel in the image belongs to the airplane category. So we do know that dark blue is for sure part of the background and dark red is for sure part of the foreground. So we can threshold this map into 3 different regions. The first region is illustrated in green here, is what we call the high confidence foreground, so very high scores from the prediction of the network. The second one is the high confidence background, illustrated in blue, where it's a very low value near 0, so we can threshold essentially the score map with very extreme values to identify these 2 regions. And then what is left, illustrated in red here, is what we call the uncertainty region, which is the region that the network is have a mixed value like around 0.5. So we need, our idea is, let's classify this region here in red based on the information that we can get from the high confidence region. How do we do that? We get this high confidence region that's now illustrated in gray here in this image, and we sample initial seeds from this region randomly. Uniform distribution we use, and we randomly sample some seeds that we grow from in a region growing procedure that is very similar to the concept of superpixels in the sense that you can think of each of these seeds inside your high confidence region as an individual agent that is searching for neighboring pixels that share the same color as them and they're very nearby and connected to them. So what happens is that then those seeds, they grow based on the similarity criteria, as illustrated here in this animation. But then if you do that only with a single set of seeds, can happen what this animation is showing, that yes, you can recover some details like the front of the airplane, like the wheels, but you can have some false positives leading to mistakes like the ones near the wing of the airplane or near the back. So that's what comes into place, what we call the Monte Carlo aspect of our method, in the sense that we draw multiple sets of seeds randomly. So instead of only having the set of seeds here illustrated in blue, we can grow, for example, with 3 different sets of seeds randomly selected, like the one illustrated in pink, in yellow, and blue here. And this way you can filter out the impact of the false positives because they're going to show up in only a few iterations. So if you run multiple iterations and take the average at the end, you can recover very well the ideal segmentation, the very fine segmentation that you would like. But this is the basic idea of our method, and then we presented this one in the ACCV conference. It's available, the paper, at our website, and I'm going to provide the link afterwards. And in terms of results here, just to quickly illustrate, we evaluated in 3 different data sets. We first evaluated the COCO. The issue with the COCO data sets is that you can have ground truths like these ones here that are very inaccurate. So sometimes you would get a refinement that looked better, but then the evaluation, the metric would say it was not better. So this is a problem of the data set as well. And then we evaluated the Pascal data set. We saw that the average metric didn't change much, but if we take a look at the boundaries specifically, there were significant improvements. It's illustrated here in this plot. And then afterwards, we evaluated the Davis data set. The Davis data set is the best one in terms of quality of ground truth annotation. It's very fine. And then here we observe larger improvements compared to the symbol here that we have in this plot, in blue, the network alone, in red, the refinement using just like superpixel majority voting, and in green, refinement using our method. So we can significantly improve, especially near boundaries, the quality of segmentation that you would have. And comparing to the baseline method, that's the conditional random fields that I mentioned, if the conditional random field is fine-tuned specifically for a network like the deep lab here, specifically for like the Pascal data set, it can provide performance a little bit better than ours, so 3.9 improvement versus 3.1 improvement. But if you do go to another scenario with a different network on a different data set without changing the parameters of this CRF, its performance decays significantly. Like you're going to have an improvement of only 2.7%, while ours, because it's more unsupervised, it does not rely on task-specific or network-specific, dataset-specific tuning. We have still the same kind of improvement in terms of segmentation refinement. And also in terms of runtime, it's very on par with the other methods. And we can increase the amount of multiple iterations that can provide a little bit further improvements in terms of segmentation quality or refinement quality without increasing the running time. It's still about 0.5 seconds because you can run on parallel each of the Monte Carlo growing iterations. For a reference, the CRF is 0.8 seconds per image in the Pascal, so we are a little bit quicker than the CRF, and we have the plans to make GPU implementation that would make very real-time method. Because images illustrate much better all the things that I'm trying to say as a metric. Here are some examples of details that we can recover. So the third column illustrates what is the prediction from the network. Then we have in the last column the refinement that we can obtain using our refinement algorithm that can recover details like the train structure, the hair, or the fingers of this man. The other methods illustrating the other columns are not able to recover, and the same for these birds' wings. So then the idea is to combine the RGR algorithm with the fully convolutional aspect, fully convolutional networks to do the flower detection. We can make another break here quickly in case anyone has any quick questions about the refinement algorithm or the idea of the fully convolutional networks.
Okay, and there, I had not caught a question in the question and answer box from the previous section. So this was a question from Long. Did you actually count how many flowers were in each image? And remember, this is about part 1.
That's a good question. What we have been trying first is what we have called the flower detection and segmentation. So it's sort of the first step towards the blooming test estimation. So once we have then the correct detection segmentation, we can estimate the actual amount of flowers based on the area that you have of flower pixels in the image, or some sort of correlation of the whole area of detection in the image to the what you would have like from the space line from someone estimating actually in the field what was the blooming phase. That's what we have in mind as a future.
Okay. And then a question in the group chat is, was there not enough data for mask RCNN?
So the master CNN follows the other approach that is possible. It's like an open question, what is better to use? Either have like an end-to-end fully convolutional network, which is more like the deep lab and these other networks follow, or to have structures like the master CNN that rely on region proposal networks. And the thing is that also we started to do this development before the master CNN was available. So that was also one reason that we opted for the deep lab approach. And the master CNN, then when it can sometimes generate better results, so to say, but then with the region proposal networks, you start to fall into the other problem called the non-maximal suppression, which is an extra parameter that is hard to adjust. So there are pros and cons for both approaches, using region proposals or using fully convolutional networks. Right now we are using the fully convolutional networks, but we plan to explore as well the master CNN to see how it looks like.
And then question from Zach, can you comment to Philippe, can you comment on how it does when instances of the same class border one another?
So this is one scenario that I actually think that it's gonna be, well, it's hard to tell, but I have the feeling that the fully convolutional approach has less problems than the region proposal networks, because you would have the issue of the non-maximum suppression, that you could actually have some two detections overlapping from different categories, but you would have a suppression that would consider as only a single detection. So here we have the prediction per pixel, essentially, which wouldn't fall in this kind of problem.
Right. So at this point, you're finding pixel level detections now.
Yeah, that's what I'm going to talk about now, combining these approaches for the flower segmentation.
Okay. All right. Let me just check the Q&A box. Okay. I think we're probably good to keep on going then. All right.
All right. I'll make sure to check the chat as well afterwards. So combining all those things to do our second method, our current method for flower segmentation. So the basic idea is, let's explore this end-to-end fully convolutional network. Let's refine its output with our algorithm to get then this kind of detection where from the input we can say where specifically are the pixel composed flowers. So first thing, we have to take care of the data sets. As promised, here's a little bit more details of the data sets that we make now publicly available. 4 different data sets, 2 of them of apple flowers, 1 of them collected without any sort of background screen. It's like sunny weather here. Another one is with a background screen, blue specifically. And then the other one is of peach flowers that are significantly different color. And the 4th one is of pear flowers. The pear dataset and the peach dataset were collecting a different type of weather, more overcast, because this is important to evaluate the robustness of the detector with respect to changes in illumination, acquisition conditions, and so on. For all these datasets, we have very high resolution images, as specifically mentioned here in this column. For the first image, 4K, for the others as well, over 2,000 pixels of resolution. And this is the one example of the accuracy, the quality of segmentation of our annotation that we provide together with this data set. And then another problem here for applying the fully convolutional networks to our scenario is that as I mentioned, we have high resolution images. If you apply them directly, what happens is that it quickly scales up out of memory regardless of how good your GPU are, because you have like 2,000 pixels per 1,500 pixels. You start to build a lot of convolutional maps, and then at the end, your memory blows up. So the basic idea then, all right, let's split the images and evaluate smaller patches of them. But if you simply do that, like evaluate each patch individually and combine the outputs together, stitching them, you run into boundary artifacts, like the ones illustrated here in blue. That would be essentially these detections most of the time. So to overcome this limitation, we have a rather simple but effective approach that we simply pad those portraits that we split the image into smaller parts. And for each smaller part here, which are illustrated like in this dashed red block here, we add a certain area around it that belongs actually from the neighboring portraits. So we evaluate then this padded portrait with the network, get its output as illustrated in the mid block here. And then we throw away the padded area, discard it, finally then combine this prediction from the network without boundary artifact into our final square maps. So by doing so, like the example that I had the boundary artifact before, now that I have the padding, I can recover a segmentation, a prediction on the network that doesn't have those boundary artifacts. So summarizing here the pipeline that we currently have for this flower detection network, flower segmentation network, that we first split the image into smaller blocks. We evaluate each of these blocks with our fine-tuned network. This fine-tuned network will provide the likelihood, its prediction for the foreground or flower category. Analogously, it will also provide you the score for the background or non-flower category. And then we combine those scores using our refinement algorithm to get a boundary accurate segmentation of the flowers in your image. So the question is, how do we fine-tune it? So with a little bit more details compared to what I talked before from the previous method. So again, we train it only in the Apple A dataset, the one with the apple flowers on sunny weather. Still have the same problem that we have only a few examples of portraits with flowers. So we perform the same kind of data augmentation of mirroring horizontally and vertically to have 4 times the amount of positive examples. We use the DeepLab network. It's the DeepLab version 2 for those of you that are familiar with the thousands of different versions of DeepLab that we have right now. The large field of view one was the state of the art in the middle of the last year. Yeah. And it was originally pre-trained in the ImageNet, as it happens for all the networks, and it was fine-tuned for the Coco stuff. We chose this network because the Coco stuff had some classes like leaves and flowers that we could use as a starting point, but it's a very poorly annotated in the Coco stuff. You have flowers that are annotated together. Leaves is a whole mess. So that's why we have to actually fine-tune the network specifically to detect flowers only. There are some more details that I mentioned it like more in the paper, like the fact that we use portrait scaling for training, like the same way that DeepLab does. So I can talk a little bit more about that if you guys want. We use a P6000 GPU, 10,000 iterations. This is the way that we get in a network that can provide detections for whether you have flowers or not, and trained on only the APOA. Then we evaluated this network in the test set of the APOA. That means images from this data set that were not seen during training. We have 83% of F1 measure, but it's important here that the metrics now are computed per pixel. This is significantly higher than the evaluation for bounding box or per Superpixels, where we are using to see like performance in the 90% range. So if you get like data sets like the COCO or so on, like for segmentation, you see like performance 40% range, 50% and so on. So it's a pretty good result. And then we evaluated in the other data sets to see how well the network can generalize. We have for the FOP here, it's more than 75% of F1 measure as well. Most of the mistakes, they happen with small leaves that are very highly illuminated, that are shining from the sun. This is a limitation that we plan to address, but still most of the detections, as you can see here, are in blue, which is good. And what's more, what made us really happy is to see the results more in the other data sets than each one, because the flowers are significantly different. As I will show in metrics, the HFCV color based on the method completely crashes in this scenario. Ours still have good performance. Same for the per data set here. Both of them acquired a different weather conditions, so it shows some robustness against acquisition conditions. In terms of metrics here, we have the comparison against our previous method, which was significantly good when we had good Superpixels. And we do significantly better than our previous method, sometimes 20% improvement, sometimes 15% and so on. And as I mentioned, if you have only like what the baselines did, only color based, if you bring the method training the APOA to the pitch data set, you have near zero performance. It simply doesn't know that these are flowers at all. It's completely lost. And another interesting thing is that these results here are with the same configuration that was trained for the APOA data set and simply applied to the other data sets. We can further improve the performance in the other data sets if we simply think about like in the application that you would have a tablet with your image. You can have like a sliding bar where you can further adjust like the thresholding parameter that guides the refinement algorithm. With one example of image, you can visually see the impact if further improve this result. This is something thinking more about in terms of application aspect. I will show more examples of qualitative results at the end during the Q&A. I'll have the videos running while you guys ask questions about it. So just then to wrap up, I'll talk a little bit about our annotation to how we did annotate those data sets. Because at first, as I mentioned, we annotated the data sets with superpixel annotation. So that meant we had to select the pixels that contain flowers. So I had to select manually through weeks of work, 5,000 pixels in this 447 images. That took a lot of time. So if you think about how do we annotate the pixel segmentation images, image annotation for segmentation, pixel accurate level, it becomes unfeasible to select all the pixels. It already took lots of time for the superpixel selection. Imagine selecting all the pixels. Commonly, what people do is they do try to draw polygons around the objects of interest. But as you can see here, these are examples of annotation of the COCO data set. The polygons, if you don't spend enough time selecting a lot of vertices, you get some kind of coarse ground truth like this. So if you think about the structure of a flower, that can be significantly complex. That would take a lot of time to annotate with polygons. So it would be more likely that someone would do more like a lazy job and provide bad segmentation methods. So that led us to explore our refinement algorithm to do annotation. Essentially, the idea is you provide, as illustrated here, some lines, scribbles inside the flowers to say what are flowers, and scribbles in red outside to see what are part of the background. And based on this information, you can use the refinement algorithm to grow into segmentation methods. So it's a much more user-friendly way of doing it. But at first, the way that we are doing is that we first drawing on a tablet, hop into the computer, running the refinement algorithm, then we saw that we did a mistake. We have to go back to the tablet, annotate, bring back to the PC. That was a pain. So that motivated us to develop a web-based tool that we are going to be presenting in the WACV now in January for this image segmentation annotation. We run some experiments that are detailed in our paper. It's like 20 seconds faster than the average time took for the COPA dataset reported in their paper, like 60 seconds per object that we require. And then our hope is that by making this publicly available, we'll help the computer vision community to annotate more image segmentation datasets with good quality and at a lower cost. Because right now the way the things are is that people have to spend quite a lot of money, like in crowdsourcing tests, or even companies specifically providing the services of annotating datasets. And if you want a large dataset, that means like thousands of dollars. And the refinement algorithm is specifically suitable for this kind of test because it doesn't require any training. So it's essentially, it just need examples of what are part of each object and it grows from them. As illustrated here in this image, that you have these variables for background, for the cat in dark red, for the chair in red, for the TV in blue, and from those simple inputs, you can grow into the massive illustrated. So basically, a basic overview of the functionalities that you have the possibility of drawing with what we call the pencil, which is like scribble, very quick and coarse that you don't need so much precision here in those areas. Or for areas that is more like squared or more thinner, that you need higher precision, you can draw straight lines. You can correct your mistakes with an eraser. And then you can select multiple levels of thicknesses because essentially to do a thicker trace, that means you have more seeds to grow from the refinement algorithm. So you're giving higher emphasis to, hey, this should be part of this category in this image. And then you can associate each line that you're drawing to a specific category. And based on this index, the algorithm will grow into the segmentation for each specific category that you have in the image. Then there are some visualization aspects here that sometimes you can have low contrast image. So you essentially can change the opacity, transparency of the image and the mask for better visualization. This is just a full example here of quick annotation. That you have the scribbles that you do for the airplane, for the background. And this is enough information for the algorithm to grow into segmentation mask. Here are some examples of the kind of annotation that we can get from the users. So you can see the bird example, or if you have multiple classes like the baby and the cat, or even for complex scenarios like this bicycle here, that's more a complex structure, it becomes a matter of only providing more traces, but you can still reconstruct a pretty good segmentation. So finally concluding here, what I expect you guys were able to grasp here is that the CNNs, they're pretty amazing for some image classification, some other tasks. But if you want like segmentation tests, there's still room for improvement. So you either making the CNNs better or exploring like post-processing algorithms as we did with our refinement algorithm. For the flower detection and segmentation specifically, we made those data sets publicly available because there weren't any data sets specifically for this kind of task. We provided information on how we develop a method that can generalize well for detection of multiple species of flowers, segmenting them in the images, and also an annotation tool that hopefully will help people to have a better time annotating segmentation datasets. And then in terms of future work, of course, the first thing is that we want them to correlate what we have is first step, that's the flower segmentation, to actually have the counting of flowers and correlate with the blue intensity estimation that you have from people in the field. And also having this information, and if we include multiple frames, temporal information, we can, one, have more consistent detection over time, and also build up like a 3D mapping of what you have in the whole orchard, where are the flowers and so on, and think about future applications like maybe automatizing the thinning process and so on. So I'll open up for Q&A, and here are some videos with the detections that we have and the 4 data sets that I mentioned with our query method. So if you guys have questions.
Yep, okay.
Concerns.
Okay. Okay, we got a couple questions. This is from Tom Kahn, down in South Carolina. So apple, peach, and pear flowers do not open at the same time. Do you expect that this technology will be able to differentiate between blossoms at different stages of development? So I don't know if I talked to you about this, Philippe, the pink bud stage versus full bloom. Or
so it's actually, we talked a little bit about that right now we have on the screen, I think, one example of each data set that all the mistakes that we have, things that we don't detect are the bugs, because
right.
we simply didn't have this example in the training data set. So if we want to detect them, it's just a matter of having a few examples and it will work fine. Or if what I could think of, if we want to differentiate between the different stages, then we can have a multi-class network. So right now we train for a binary case, but we could be classifying to different scenarios. Just require more specific annotation and training. But the same type of pipeline should work for them.
Okay. And then this is a question from Trenton. He says, you're originally motivated by counting blossoms, but in your tool, it seems that multiple of the same object are being combined into one segment. Very closely related to Zach's question.
Yeah. So what we currently have in mind is that because the images are at a certain limitation in terms of depth, each image is evaluated in a specific tree, in the specific row. We can have an estimation based on the area. What is the average area of your flower, and correlate to the total area of detection and the image. And then we can also think, if it's necessary, we can see that this is not an accurate approach, we can think about trying then more like instance segmentation of actually detecting the separations between each of the flowers being detected. So we have these two possibilities that we plan to explore. If we see that this directly correlation between area and the bloom intensity estimation is not enough, then we can explore more in the direction of the instance segmentation.
Yeah, and many of these images, because now I remember, I did capture all of these images. It was a long time ago, but I did that. All these images are from video, so you could use other frames too.
Definitely. The temporal aspect is one thing that we truly believe that we can explore much more to improve the segmentation in general, and also differentiating between different instances. And also there is another possibility, which is like related to the work of other guys in West Virginia. I think it's Provcar that I saw in the IROs, that they have a classification network to detecting clusters, how many objects, how many fruits they do have. So this is something that we can think about as well. We have clusters, we can have like a sub-network just counting the amount of flowers that we have in clusters. But first, I think it makes more sense. Let's try to correlate the area, because if this is enough, the simpler approach, then we don't need any reason to actually go in the more complex direction.
Okay. Are there any other comments? I mean, this flower detection question can be, in practice, evaluated a couple different ways. That's true.
Especially in terms of the temporal, because they have different angle views. So in some angles, you might see an overlap. In some other ones, you'll see that there is actually a gap. Then you can construct a better segmentation from that. So indeed, the temporal thing is probably the most promising thing to try right now.
Okay. Well, it's right at our ending time, so I'll close by saying thank you very much, Philipe, for giving a talk, and thank you everyone for joining us.
My pleasure. Very happy with the opportunity. Thank you.
You're welcome. And if you want to find the materials for the talk, you can go to our website, IEEEagera.com.
Just mentioning here again that I'll talk with Amy as well to make available there. We're going to make available both the RGR algorithm, the refinement, and the annotation tool, so we can link there to the web page, the links where you can find this too.
Yeah, and I can update that later. If you want to find out when the next webinar is, you can talk to me about joining our technical committee or follow us on Twitter at AG Robotics TC. Okay, thank you all, and I'll see you next time.